All right, so this is the limbic system. So this is the last of the 5 videos. And the first thing I want to cover, so I know I have enough time for it, is this is a great way to study or to understand how to use optogenetics in a good setting, or in a where I'm looking for, whatever. So this is a great example of optogenetics in technology and neuroscience. So if you take a box, and there's 2 chambers of this box, and you take a mouse, here's a little mouse, here's whiskers, and his tail, and you take this fiber optic optogenetics cable. This cable, so this optogenetic cable, this fiber optic cable, is connected to nucleus, let's call it nucleus X. And we want to determine nucleus X. We want to determine the overall effective activity in nucleus X, right? So if we turn on this fiber optic cable, so if we send some information down its wire, it increases the activity of nucleus X. And we think nucleus X is responsible for emotion. So if the light is off, so I'll draw it like that. So if the light is off, the mouse I'll draw it like that. So he still has the cable, but it's not on. So the mouse kind of freely goes back and forth between this box. Kind of chooses where to go, but if you graph it out, time spent in the left and the right boxes is pretty much equal. So what this means is this mouse has no preference between the left and the right sides of this chamber. So the left and right sides of this box. When you turn on this fiber optic cable, so when you send some light down its way, so you're basically increasing the activity of nucleus X in their brain. Let's say you do this experiment and you find that if the light is on, let's call this left and right, let's say you actually see a lot more, the mouse spends a lot more time in the left chamber than the right chamber. So what this means is that the mouse prefers the left chamber. And one thing that's crucial to this experiment is that the light is off when it's in the right chamber. So I'll say in the left chamber, light on, and then the right chamber, light off. So what's happening is the mouse is spending more time in the left chamber, meaning that it prefers to be in the chamber in which the light is on. So what we can get from this is we can say the neurons in nucleus X must be responsible for, or activity in the neurons in nucleus X must be responsible for positive reward, or behaviors that, or neuronal activation that results in positive emotions. So this is a way to use optogenetics to determine the function of specific nuclei in the, let's say this is in the hypothalamus or in the basal nuclei of the emotional circuit. So what we're finding is that we can use optogenetics to determine whether or not a mouse likes that nucleus being turned on. So that's just a great way to show that we can use optogenetics in a real-world setting and to solve these questions from various different topics in neuroscience. But, so where do we start when we talk about emotion? Well, what is emotion, first of all? Emotion is not only how we consciously feel, but the physiological changes associated with those emotions. Associated with those emotions. So if there's something like pain asymblia, that disorder in which somebody can describe what is happening to their hand, or what describes some outrageously painful stimulus without actually experiencing the emotion behind it, what they have is a lack of the physiological changes associated with emotion. They have a lack of this like increased heart rate and blood pressure and sweating in response to pain. right? So they don't really have this emotional response. So emotion, again, is not only how we consciously feel, like when you feel sad or when you feel nervous, but it also describes the physiological changes associated with those emotions. So we can categorize emotion two different ways. So emotion can be categorized based on its valence. And I don't want to say that. Oh, valence and arousal. So valence is whether or not it's positive or negative emotion. So something like being sad is obviously a negative emotion. Arousal is whether or not we have high amounts of brain activity, more specifically high amounts of emotional circuitry activity, or low amounts of activity. And the idea here is that every emotion can be plotted somewhere along the spectrum. So if you take valence, if we say these are positive emotions, these are negative emotions, this might be different than the way it was represented in class, axis-wise. But if this is arousal, so this is high arousal, and this is low arousal, we can say, okay, what's a positive emotion that's also high arousal? Something like euphoria, right? So when you take something like a drug like cocaine, increases your arousal, and it is a positive valence. Like it simulates the feeling of reward, or something that's rewarding or makes you happy. Whereas something that's high arousal but low valence or negative valence would be something like anxiety. So, often people say the only difference between euphoria and anxiety is whether or not you feel good. So euphoria is this high arousal state of really happy. Anxiety is this high arousal state of really unhappy or really distressed. Something that's positive valence but low arousal could be something like calm. So if you're in this really calm state, it's a good feeling, but it's also very low arousal. You don't have a lot of activity in your limbic system. Something that's low arousal but negative valence would be something like depression. So something in which, a disorder in which you feel negative emotions and you feel this low arousal. So, an inability to want to do something. This is where you get something like passive coping mechanisms. Whereas with anxiety, you get things like active coping. When you have a depressive episode, you don't hyperventilate, right? Active coping. So this is a way you can categorize emotions. And I'm forgetting what's in this. Oh, right. So what we talked about next, after we categorized emotions in this way, we talked about the amygdala, because the amygdala is important, or is necessary, for the integration between sensation and the emotional responses, whether they be physiological or behavioral. So integration between sensation and then emotional responses evoked by those sensations. The amygdala is also responsible for associative learning. This is that Pavlovian stuff where if you play a tone and then you shock the foot of the mouse, soon it will experience a negative emotion just based on the tone. So you've been able to associate that pain from the foot shock with this previously neutral stimulus, a tone. So what happens is you have this neuron in your, this doesn't matter, but it's in your basolateral nucleus. And you have this really weak axon. So this is tone. This is like if you play a tone when you shock a foot. And then this is a really strong axon, a really strong connection between a foot shock and pain. So this is negative emotion. So what happens is if you pair these stimulations, this tone and the foot shock, what you get is an upregulation of AMPA receptors at this dendritic tree of this pyramidal neuron in the basolateral nucleus. So this is in the basolateral nucleus of the amygdala. And you get a strengthening of this axon that's carrying tone information. So eventually, this axon is now strong enough to produce this behavioral response, this negative emotional response, itself, without the presence of the foot shock, because you've strengthened this connection. And so when I say basolateral nucleus, what am I talking about? Well, there's three main nuclei in the amygdala. There's the basolateral nucleus, which is the big one. There's the medial nuclei. And there's the central nuclei. And they're all interconnected with different parts of the brain. So this goes through thalamus to get to cortex and back again. So most of these systems are bidirectional. The central nuclei project to and from both the hypothalamus and brainstem centers. So in rats, like if you shock their foot, what happens is you have information coming in from, your nuclei in the pain pathway projects to the basolateral nucleus. These neurons project to the central nuclei and produce what's called the freezing response based on the brainstem reticular formation, which is a way to assess negative emotion, and into the hypothalamus, which is responsible for, remember, the hypothalamus is the master regulator of the autonomic nervous system. So this increases heart rate, increases blood pressure. It may, it may dump epinephrine into the bloodstream, stuff like that. So this is where you get that integration between a stimulus, like pain, and a response. So the central nuclei are connected to the hypothalamus and the brainstem. The basolateral nuclei are connected to the thalamus and the cortex. And the medial nuclei, and this gets back to our olfactory lecture, these are interconnected with the olfactory areas. Right? And this just further emphasizes the fact that olfaction and emotion via the amygdala are very well interconnected. So olfaction is able to produce emotions in response to stimuli a lot quicker and a lot more effectively than something like sound or vision. And I think that's all I have for you here that's best explained in a video. I think the study guides are going to be a lot better at some of the more nitty-gritty, what we expect you to know, what we need you to know. But this hopefully gives you an idea of why we do things and how we study emotion, the main structures responsible for emotion and how they all fit together. So if you have any questions, again, you're always willing to email me, drg1997 at rams, the rest. And if this is the last time you ever hear from me, thanks for being a fun class. This was a great experience to TA for you guys. Thanks.